In this lecture, I want to cover some last few topics, some cleanup for the NMR section. So the first thing I want to look at is the coupling constant in a bit more detail. This is also called J. Sometimes the bond, shoot, I can't remember if it goes up here or up here, but I'm just going to write it big next to it. Just slipping my mind right now. With a number. So J is sort of the label. The label of what we would say J equals the coupling constant equals something. And then 3 is the number of bonds. Now, what we get by considering J is we start to understand something about what's called a spin system or a coupled system. And so let's look at an example where we have some, a fairly simple molecule that we can look at is diethyl ether, where we have two hydrogen environments, an HA and an HB. There's 4 HBs, one on the left, two on the left, 2 on the right. And then there's 6 HAs, 3 on the left and 3 on the right. And so what we would say is that HA and HB form a spin system because they are coupled. Now, what does that mean, coupled? And what does that mean, spin system? Well, if you looked at the NMR, let's just look at this. The 1H NMR, we would see something that looks like this. We would see a signal with 4 peaks. Going further to the right, then we would see a signal with 3 peaks. And now, if you recall from our discussion about common multiplets, we would call this a quartet and this a triplet. Now, what is J for the triplet? It is the distance between here and here. And so we could label that distance between any two peaks of a multiplet. Okay. And it's constant. It's saying that for this quartet, the distance between any 2 peaks is J. Now, what's really cool about this is that for this particular set of peaks is that the coupling constant in the triplet is the same as the coupling constant in the quartet. It turns out that for coupled systems or coupled signals, the coupling constant is the same. Now, I haven't really given you enough information to understand this definition fully, but it allows us to break down the word coupling constant a little bit. So we have coupling constant, that implies same, and coupled appears, let's circle the right word for parallelism. Coupling refers to coupled. Now, what does it mean to be coupled? Well, what that means is that one chemical environment is causing another chemical environment to split, and it actually goes both ways. A causes B to split into a quartet, and B causes A to split into a triplet. So let's phrase it this way. 2 signals are coupled if the 2 chemical environments split each other. Now for this particular example, we have HB, 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 HB. Then we have HA, 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 HA. Now, A has 2 neighbors, depending on where you look. It has 2 neighbors, and that's 2 times HB. Similarly, B has 3 neighbors, and it's 3 times HA. So one causes the other to split. The other causes the first one to split. And we say that A, because there's 2 times HB, then HA forms a triplet, and B forms a quartet. That's following what's called the n+1 rule, where the number of neighbors plus 1 equals the number of peaks that you would observe in the multiplet. Okay, but furthermore, we must emphasize that HA is then coupled with HB. That's all that's saying. Whenever you see splitting, it's from neighboring protons causing an alpha to beta shift. Now, what's interesting about the way splitting works is that it goes both ways, right? The HAs coupled split the Bs, the HBs split the As. And then we say that those two things are coupled with each other. Now, what I'm trying to emphasize is that in the multiplets, the two, the coupling constant will be the same. I would have preferred to say this. The coupling constant J will be the same in both multiplets. Okay, kind of awkward phrasing there. So the coupling constant's the same. Now, what is a typical coupling constant? So we can look at this with a fair degree of precision with a few decimal places to really allow us to kind of navigate a spin system that is a system where we have all of the hydrogens coupled to each other. But a typical coupling constant is about 7 hertz. Now, hertz, I'm going to write this in a different color. Hertz, why not parts per million? If we're going to go to the trouble of using parts per million along the x-axis for the chemical shift label, why not parts per million for the coupling constant label? Well, it turns out that the answer to this question is that the Hertz distance doesn't change with the external magnetic field. So I'll just label that H0 for external magnetic field. So that means when we go from a 300 megahertz to a 500 megahertz, the coupling constant value in hertz will remain the same at about 7 hertz. Actually, the parts per million value, as you increase, H0 will go down because the influence of having an alpha state and a beta state flipped will thereby be a little bit less. But you can actually, it's actually will stay constant if you focus on the hertz value. So it's a little bit backwards. And I'm not going to go into it too much. I'm just going to say that for very important reasons that you should be aware of, the parts per million value will not change for the chemical shift. But for the coupling constant, the hertz value will not change. So it's really interesting. So we choose to label our coupling constant values in hertz and then our chemical shift values, delta, in parts per million. So I realize I'm going to leave you hanging a little bit there in terms of why, but I don't want to extend this module too much longer. We can talk about that later if you're really curious. We can go through some of the math. It's not too bad math. It's just I want to save time. Okay. One thing I want to emphasize before we move away from coupling is that it's just general. It's not subject to just being hydrogen atoms, but atoms in the same chemical environment do not couple each other. And that's because, just really quickly, that's because they're all being excited by the frequency causing the one to flip. So what I'm saying is HA won't couple with all the other HAs because if you excite one HA, you excite them all. And if they're all excited, they're all in then the beta state. And so they're not going to be able to couple each other. They're all in the same state. Okay. Now, what that means is that if you've got a molecule like this is just benzene, and we've labeled this by saying that it only has one hydrogen signal because the symmetry of the molecule was such that every hydrogen is actually in the same chemical environment. Now, if you just look at one of the hydrogens and count bonds, you have two hydrogens that are 3 bonds away. So perhaps you would expect this to be a triplet for that one signal. It's actually incorrect because they're in the same chemical environment. It's as if, in terms of neighbors, they're not even there. So this actually is a singlet. And that's because everything's in the same chemical environment. Okay, so it's a singlet. Let's look at another example. Let's delete those double bonds and talk about cyclohexanes NMR properties. Okay, so cyclohexane, we've talked about this one as well. It has, by this perspective, it has the exact same sorts of symmetries, right, as benzene. It just has double the number of hydrogens, right? There's a hydrogen up and a hydrogen down. And so we actually observe a singlet for this molecule. And I know that chemical shift. That chemical shift is 1.38 parts per million. So that's due to symmetry, right? Well, no, let's think back. What do we know about cyclohexane from Organic Chemistry 1? Is it a simple flat structure where the top side and the bottom side are identical? Well, no. Remember, we spent an entire exam on this. Cyclohexane is a chair. So remember the chair structure? Oh gosh, I can hear everybody groaning in enthusiasm to draw these chair cyclohexanes again. Okay, so here we have our chair. Now what we're going to do is add the positions to each of the carbon atoms. Not too bad. It came back for me pretty quickly. Sorry. I know this is my job. Okay, I'm going to give myself a little bit more clearance so that I can write the hydrogens. Okay, let's get serious now. The chair cyclohexane kind of complicates things for us and kind of is an understatement here. The reality is that the cyclohexane does not possess the same degree of symmetry as what we saw with benzene. Because it's not flat, the top and the bottom face are different from each other. That is, in one case, you have an axial group. In another case, you have an equatorial group. So I'm going to label that A and E. Now, it turns out that it doesn't look like it, but you can actually spin this around and show that the E's are in the same chemical environment as the other E's, and the A's are in the same chemical environment as the other A's. So my point is, there's only 2 chemical environments. HA, which corresponds to the axial hydrogens, and HE, which corresponds to the equatorial hydrogens. Okay, so if there are two chemical environments, why do we only see a singlet in the NMR spectrum? Well, that comes back to the other fun thing that we learned with chair structures. They flip. We can flip chair structures around. So why only one signal? Because chair flipping. Let's look at this in a bit more detail. If I draw a chair and consider only two hydrogen atoms, one equatorial and one axial, I'm going to label the equatorial one yellow and the axial one green instead of HA and HE, because I'm going to flip this. I'm going to undergo a massive conformational change to flip the chair structure such that we now have this as our molecule of interest. And if we have that as our molecule of interest, at the same carbon, furthest to the right, we have two hydrogens. Now axial is pointing up and equatorial is pointing down. When I consider my highlights, even though the yellow started equatorial, when you do a chair flip, you flip every position from axial to equatorial and equatorial to axial. And so my yellow and my green labels, the yellow is still on top. It's still the more upward facing group, but now it is axial instead of equatorial as a result of the chair flip. What this does is this says that sometimes yellow is axial and sometimes it's equatorial. And that actually is true for every one of the 12 hydrogens on cyclohexane. Sometimes the H's or H atoms are axial and sometimes they're equatorial. Okay, so how fast does this chair flipping occur? What I want to emphasize to you is that this is fast at room temp. At room temp. Okay, so at room temperature, the chair is kind of flipping and flipping and flipping and flipping and flipping. And so what the NMR does is the NMR is kind of like an old-timey camera. It has what's called a shutter speed. That is, imagine the old-timey photographer. He's lining up to take the picture. He's got the big light bulb and he snaps the film. What does the picture look like if somebody's going like this the whole time? It's like a blur, okay? The NMR has a shutter speed like an old camera. As a result, the constantly moving molecules will create a blurry image. A blurry image. That is what you get is the axial and equatorial will average into one singlet. Because chair flipping is happening so fast, the camera just takes a picture and the hydrogens are kind of somewhere in between axial and equatorial. It makes kind of a Gaussian distribution based on where things are at in the midst of their chair flipping. Okay, so it's, again, this is like taking a picture of something moving. You know, it's super annoying. Like I've got these adorable kids and they're always moving when I want to take a picture of them, and then, you know, I get like these blurry shots. So I'm just like, hey, everybody, calm down. So how can you say that to a and if, you know, if they calm down and everybody stays still, like holding a pitchfork. Sorry, that was probably a weird face. Like American Gothic or whatever. Everybody's standing still. Then you can get a nice picture with good focusing and see all of the detail. Okay, how do we do that with molecules? We can't tell molecules to sit still. Sort of. We can slow them down. Okay, if we cool our NMR sample, chair flipping slows down. And we observe two signals. Let's not worry about what their multiplicity is. Just trust me, we observe two signals. We know a lot about these signals. What we know is that one has a chemical shift of 1.62 parts per million, and the other one has a chemical shift of 1.14 parts per million. So if we really cool things down, and let's cool our NMR sample to about minus 60 degrees Celsius, okay? And we can do this within the NMR probe. It's called variable temperature. A lot of times we actually heat up our samples for the most part to get them to do things faster and get to a nicer, more averaged spectrum. Speaking of average, let's do a quick exercise. What if we take 1.62 plus 1.14 and we divide by 2? If we do that, we get the number 1.38. If we keep the unit parts per million, that is the room temp chemical shift. And so our shutter speed experiment allows us to see the dynamics of molecules using a technique like NMR spectroscopy by taking advantage of the fact that chemical environments might be very distinct and different. For a molecule sitting still but moving fast, that molecule is rotating bonds in averaging chemical environments. That allows us to see why things like CH3 groups, for instance, actually provide only one signal despite having 3 hydrogen atoms. Okay, so that'll do it for the non-lab portion of this section. I still have a few more things I want to cover, and I'll save those for the pre-lab because they're more experimentally relevant, and so you get more out of them seeing them within that context. So just a few things like the solvent choice and how to actually run an NMR experiment, I think are really important. And like I said, I'll just save those for the lab component pre-lab. Okay, so with that, we'll end the first module for the course on NMR spectroscopy.